Hello. Welcome back to the continuing lecture in investment analysis. So, in our, continuing on with our last, last session, where we have the regression result of the Google, the excess return on Google over the market excess return. And actually, if you plot the regression result, right? I mean, of course, the regression result is basically this regression line, the slope of the scatter plot. And instead of, just, having the summary statistics, I mean, the summary statistics is not shown here, but yeah, here's the summary statistics. This is the basically, graphical representation. It's called, these, blue dots are, called the scatter plot, because it's scattered plot of the data. Now, and of course, you see there's a very clear and obvious and very conspicuous positive trend, or upward trend, right? And the best fitting regression line is, of course, automatically found by Excel, but the technique to find the best fitting regression line is called OLS, ordinary least square method. And of course, they are not all falling exactly on the regression line, because you're fitting the line to the data, not the other way around. In other words, but again, if the security market line, and this is called security characteristic line, not security market line, because you're regressing the excess return over market excess return. But the idea, but anyway, the idea is, it is unless you are generating data from an equation, right? The equation of the line is given, and you just plug in x values, from 0 to let's say 0 to 50. I mean, to make 60 data points, 0 to 59, it has to be. But anyway, if each x value is an integer, right? Positive integer, 1, 2, 3, 4, 5, 6, and all the way to 59, we have 50 x values, and there will be matching corresponding y values, 50 of them, 60 of them, I mean. Now, in that case, those plots will fall exactly on the regression line, because those y values are generated by the given equation, right? So, but the reality is we're not given the equation of the line. We are given the data plots, the scatter plots, and we are through regression, we're trying to find the best fitting line. Okay, and Therefore, R square, or the goodness of fit, R square or goodness of fit, uh, would 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 be, obviously less than 1. And in this case, actually, R square is like 39.97%, which means, 34.97% of Google's excess return variance explained by market excess return variance, which also means, 65% of variance is due to firm-specific factors or unexplained by the uh, uh, the market portfolio or index portfolio, right? That R square is, we also talked about this. R square is, and I, replicated here, is simply systematic variance or explained variance over total variance, right? And what is the systematic variance? Systematic variance is the beta, whatever, the variance explained by beta, right? So the subscript is D here, but ignore that because that subscript that was the subscript for del, but actually we are using Google, for this regression. But you understand, basically variance of the Google is related to the market variance, variance of market returns by beta. So the systematic or explained variance is beta squared times, market variance, right? And then the total variance is, simply it can be broken down into explained variance and unexplained variance. Unexplained, look, all of these, distances are basically, forecast errors or residuals, because if once again, if Google is in equilibrium, right? If market Google is in equilibrium, then all it will be, all, Google and market are, in equilibrium. They will exactly fall on the. In other words, there will be no forecast error, right? It will be exactly everything is forecasted exactly by, by beta times, market excess return, market risk premium, and it will fall all neatly on the regression line. But that's obviously not the reality. And the the variance of these excess returns, variance is, basically partly, what is explained by the market and the beta, and what is not explained by the systematic factors, where and that's why it is called, unexplained, right? Variance, and that's due to firm specific. That's truly uh, the firm specific factors, right? That is not explained by the market. So this is called summary statistic. Summary statistic. Usually, when you run regression on Excel, you will get this, summary statistic. So R square is basically the goodness of fit, right? Uh, and this R is correlation. This is, actually correlation, right? And you might wonder, the correlation squared is R squared. Um, we can check. And that's actually the case, right? That's why, uh, that's why they use R square, right? So so what is the difference between, R square and adjusted R square? I mean, think about it. If the correlation between, X and Y, if the correlation between um, X and Y uh, is, think about it. If the correlation is 1, what's going to happen? If the correlation is 1, the everything will, first of all, the slope of the line will be 1, and if the slope is 1, it will be a 45-degree slope, right? The grade will be 45 degrees, and everything will fall neatly on the straight line. But that's not, and if the correlation is 1, R square uh, is also 1, which means, there's everything 100%, the fit is 100%, right? Now, and we understand R square as, explain the sum of squares. That means explain the sum of squares over total sum of squares, right? Total sum of squares is, that means variance, total variance. And explain the sum of squares is uh, the systematic variance, right? And you remember, the formula for variance is basically, sum of squares, right? Sum of the, square difference terms, right? Divided by, a number of observations. But, in this case, you might wonder, so where is that n minus 1? Well, if it has 1 minus 1 here and n minus 1 here, anyway, they will cancel out, right? And another way to represent it is 1 minus unexplained sum of squares over total sum of squares, right? Think about it. They are, explained variables and explained um, explained errors and unexplained errors are sort of like complementary. So if R squared is the ratio of explained sum of squares over uh, total sum of squares, then uh, 1 minus unexplained sum of squares over total sum of squares is the same thing as R squared, right? Now, this R squared needs to be actually, adjusted for degree of freedom. Remember, I've been talking about when we did variance in calculating variance uh, or standard deviation. If there are n data points, right? N x number of data points, we call it n, just n number of data points, right? You cannot divide it by n, but rather you have to divide it by n minus 1. And I already explained why, because if that is not the data set that you have is not the entire data set or population, right? Um, then you are only using a sample uh, data set, and when you're using sample data set, you have to make adjustment for loss of 1 degree of freedom, which means the data set loses uh, uh, freedom freedom to vary, randomly vary. Why? Because a sample data set is not the entire uh, population. I mean, it has a limitation, right? And then also because of that limitation in uh, data set. In other words, it's a subset of the entire population, and the subset would each, for example, if I have data for Apple for the past 40 years, right? How many monthly data would I have? Of course, I would have 40 times 12, so 480 data points. If I use, if I use all, if I'm evaluating or running regression with all, or taking the variance, calculating the variance with all uh, 480 data points. That's the population, and I can divide it by n because I have uh, the Apple's monthly return data uh, has completely full range um, of values within which it can vary, randomly vary, right? But if I'm using only the most recent 5 years, recent 5-year returns uh, would have limitations, or uh, it is conditioned. It's conditioned, or it has most recent 60 data points is conditioned, has been conditioned already to uh, the most recent 5-year uh, market situation and most recent 5-year Apple's fundamentals, right? And it cannot be, the same thing as the most remote 5-year, data set, right? So the mean of this sample data set, the mean of this uh, subset of data uh, will be all different, right? And the difference terms, right? Because to calculate variance, you have to take the difference terms, right? The difference terms will, will be already, uh, conditioned by what the mean is, right? In other words, there's a because mean for this group, uh, the difference terms are already, set to, uh, vary within certain range, uh, based on what the mean of this, sample group is. Um, that's why you're, losing 1 degree of, actually the data set is losing 1 degree of freedom because, of, uh, so, then n minus 1 then makes sense, but then what is n minus k? N minus k is the k is actually the number of explanatory variables, or number of independent variables. In other words, if you have, uh, in this example, we have only one explanatory variable, which is, market excess return, right? This is, this is called, a simple regression, because when you have only one explanatory variable in the regression model, it's called, bivariate model. Bivariate meaning two variables. And why two variables? Because there's, independent variable and dependent variable. So bivariate, right? Bivariate. Now, sometimes the model could be, model specification could be, multivariate, right? Like, I don't want to, multiple regression, right? The model can be specified as y equals, excuse me, alpha plus beta 1, x1 plus beta 2, x2, and you can have as many explanatory variables as, so if you have n explanatory variables, then it will be beta n times xn, and then there will be some arrow term, right? Okay, this is called multiple regression. But again, I've been telling you over and over, if you increase the number of explanatory variables, your forecast may be more, you may have more precision and more accuracy in the forecast. The models, R square might improve, right? The models R square will certainly improve, but that doesn't necessarily mean it's the it's the best model or the most powerful model. And also, even if the fit may improve, right? Even if the fit may improve, actually, what's important is the overall, F value, F statistic, or and individual variables, individual explanatory variables, T statistic. I'm going to get to that shortly, but what I'm basically, but looking at this regression summary statistic, right? Let me clean this up. I don't want to have this. Oh, it's not. Come on. Hope I didn't. Okay. All right. I think I'll have to. All right. So, if we have three explanatory variables, right? So it's like y equals beta 1 times x1 plus beta 2 times x2 plus beta 3 times x3, right? In that case, we have three explanatory variables, and we must make adjustment for um, the number of explanatory variables, which will be which is k. So that adjustment is being made to the sum of the unexplained variable, unexplained squares, and unexplained sum of squares, and then the result of this is called, adjusted R square. So actually, adjusted R square tends to be smaller than just, regular R square. So here, our adjusted R square is 0.3385, which is, smaller, right? Smaller than just R square, and standard error of regression is 8.4. Standard error is the standard deviation of the error terms, right? The residuals, right? And which is basically due to the firm specific component, right? Firm specific. So this is the firm specific component of Google's access return. 5 years, so it's 60, observations, right? And this is between, time. The time frame is, what was that? Yeah, January 2006 through December 2010. So that's exactly 60 months, and then overall, the overall significance of the regression is captured by F value or F statistic, and which is also called ANOVA. ANOVA stands for analysis of variance, and we are actually these are all variance, right? Variances, and I'm gonna get to that later. So is this number good or bad? I'm gonna get to that shortly, but I would say it's good. It means it's this this regression is this regression is significant. I mean, this regression has significant, the estimates from this overall estimation is, statistically significant, right? and that is, let me get to individual variable, right? The estimates obtained from this regression for individual variables, right? So basically, we have, since this is bivariate, or simple bivariate or simple regression, meaning we have only one explanatory variable, S&P 500, right? So this coefficient of S&P 500 that's beta, right? That's beta, right? So that means Google's beta with S&P 500 is 1.2. In other words, that's the slope. That means that's the slope of this, right? It's the slope of this regression line, and $1.2 something, right? 2031, right? Yeah. And the alpha is 0.8751. But the standard error of beta is 0.215, and standard error of alpha is 1.09. So what does that mean? Now, think about it. T statistics is basically telling you how significant this estimate is. And if you think about it, alpha coefficient is only 0.8751, and its standard error is 1.092. So that means this doesn't seem, for 1.09 standard error of 1.09, the alpha of 0.875 is, if relatively not very reliable. If you divide this by this, then that's the T statistic, right? And I've been telling you that the T statistic, the threshold, rule of thumb or threshold for T value is 2, and greater than 2. If the T value is greater than 2, that is the proof, or that is the evidence of robust estimation. Okay, it's not a fluke, right? It's not by chance that this number came up. But look, the T value of beta is very high, 5.58. What does that mean? So this estimate is not by chance, right? If you and the P value is probability. That means probability of getting this kind of result. The probability of getting a beta coefficient that is non-zero, right? The probability of getting a beta estimate that is, different from zero falls into this, extreme, outlying areas, right? It's an outlying probability. This means, remember in the in the normal distribution, right? The outlying areas of the curve, the upper tail, lower tail, right? I mean, what is the probability of, falling into the upper tail? Like 2%, right? 2% upper tail, 2% lower tail. Think about it. The probability of falling into that area is very low. That means, if this estimate, this value is if this estimate is obtained from regression, it is significantly different from zero. In other words, think about it. There is if I got an estimate, that is, say, like 1.2, but its t-value is something like 0.8. What does that mean? It's like the probability of, it falls in the like within one standard deviation from the mean of zero, right? Which means, normally the beta is zero, and the probability of, although you got the estimate of beta estimate of 1.2, the probability of that number happening is within like one standard deviation, right? One standard deviation is like 32%, above mean, 32% below mean. So actually 42% probability is like, not even one standard deviation away from the mean beta value of zero, right? You see what I'm saying? The higher the probability, that means, there's a high chance that this estimate is purely by chance, right? But if the probability of this number happening is this low, then this is clearly an outlier. It's significantly different from the mean beta value of zero, right? And therefore, this estimate is very robust. This regression result is very robust. Okay, that's what is meant by t-statistics. Okay, we're gonna again, since we're running out of time, I will have to continue. I will have to repeat this, or revisit this discussion in the next video. But we're gonna obviously go over that again. But I'm not a very verbally efficient person because concepts like this, you have to mathematically get the intuition, right? You have to have that mathematical intuition to Otherwise, verbally explaining it is really uh, a difficult job, right? Um, so I'm gonna have to. We're gonna come back with and I'm gonna have to stop the video here, and I will see you guys in the next session. Stop recording.